Hey guys, I'm just going to do a quick little run over of some nuclear decay problems. Um, so um, we're just going to start off with a brief little discussion, then I'll show three examples of different nuclear decays that should help you with kind of the assignment. First off, we are dealing with radioactive decay here, which means radioactivity means the emission of something out of the nucleus of the atom. Something gets shot out. That's all that nuclear means, from the nucleus. Yeah. We're going to cover three types in this video: alpha, beta, and gamma radiation. There are other types of radiation that we will not cover in this class, like positron emission, proton emission, neutron emission. Actually, probably the most dangerous type of radiation, generally speaking, is probably neutron emission. But again, that's not kind of in the scope of the content of our class, so let's concentrate on what we've got. Okay, we've got three types. We've got alpha, beta, and gamma. Each of these has a Greek letter associated with it. They're named after the Greek letters. Alpha is kind of like a sideways Jesus fish without the tail connected. Beta is just like a large B, but with a little bit extra tail. And gamma is that same Jesus fish, but now standing on its head. Okay, those are the three Greek symbols, but those aren't all that super useful for us. So we're going to write these using some Latin symbols, the alphabet that we normally use. And we're going to indicate them both with the symbol for whatever particular element they are, and then we're just going to show it in isotopic notation: element or subatomic particle. So like an alpha particle is actually a helium nucleus. In an isotopic notation, we write the mass number in the top on the left, and the mass number, again, is the number of protons plus neutrons. And then in the bottom, we're going to write the atomic number. And that's kind of optional, because the very fact that this is helium informs us that the atomic number must be 2. Helium is the only element that can have an atomic number of 2. So it's a little bit redundant to write this one when we have an element along with it, but I guess you can, or you can omit it, whichever you prefer. We're going to want to keep that field though for the beta radiation, which is kind of why it's been included, because for the beta radiation, it's going to emit an electron. And this electron actually comes out of a neutron that's in the nucleus. And kind of, if you want to think about it this way, what a neutron is kind of like a proton and an electron jammed together so that they neutralize each other and have no overall electronic charge. So if that neutron decays and fires off an electron, it fired off some negative charge. Well, in order to conserve the charge, that has to leave the particle behind as a positively charged particle, or in other words, a proton. So what beta emission does is turn a neutron into a proton by throwing off an electron, by shooting out an electron. And so for our beta emission, it is shooting out an electron. So an electron is the particle being emitted, and we're going to write that just as a E to symbolize for electron. And an electron has a mass number, the number of protons and neutrons, and an electron is 0. So it's going to have a 0 as the top number. And now, as a bookkeeping measure, and this may not make perfect sense right now, but when I get into the examples, hopefully this should make some sense. As a bookkeeping measure, because this emission increases the number of protons by 1, we're going to write a -1 down here. And that way, mathematically, this symbol is going to work out really well for us when we put this into a nuclear equation. And finally, for gamma, gamma is pure energy. Gamma is not does not have a particle associated with it. It's just very highly energetic photons being shot out of the center of an atom, and typically is accompanied by some other type of emission. So if we have a beta emitter, it might emit a beta and a gamma. Or an alpha emission might be an alpha and a gamma, because that nucleus has lost some binding energy, and that energy needs to be kind of translated to the universe somehow. Can't just be lost. Energy is conserved. And so this decay can also be accompanied by an outpouring of energy. That outpouring of energy is known as a gamma ray. Since gammas don't have a particle associated with them, we're actually going to just keep that gamma symbol from the Greek alphabet as our symbol. And gammas don't have any protons or neutrons associated with them. And they also don't change the number of neutrons or protons at all. Not by themselves, they're just energy. And so there are our three symbols, our three types of radiation, our three symbols for them. Just before I move on into the actual practice, we're just really briefly talking about kind of the danger profiles of these, or what, how they might be dangerous to us as humans. First off, alpha. These are pretty large. Relatively speaking, in the world of subatomic particles, these are pretty honking big. They have 4 nucleons in them. And so if these get shot off, they're pretty likely to run into another kind of another atom. They're pretty big, and they've got these 2 protons that can carry some charge along with them, and so they can easily be stopped by other things, more or less. And so things like a thin sheet of paper would actually be enough protection to shield you from an alpha source. Your skin itself is enough protection to protect you from an alpha emitter. However, an alpha emitter can be dangerous to you if more or less it's consumed either via your digestive system or by your respiratory system, because those particular membranes are designed to transmit material. They can transmit these alpha emitters inside of your body, where the particles are then able to do some damage. So alpha, basically, a respirator protects you. Don't eat it, don't breathe it, and you should be fine. Excuse me a second. Oh, coronavirus. Sorry, I shouldn't joke about that. It's not funny, and there are some people really struggling with it. I do not, to the best of my knowledge, currently have coronavirus. Okay. Next up, we have beta emission. And beta is an electron. And that's all beta is an electron. Now, just like electricity, which is also the movement of electrons, beta radiation can be dangerous. It's a little bit more, well, alpha can be dangerous too, but beta can be dangerous to even your skin. If you get a high enough dose, you can get some kind of radiation burns and sores opening up on your skin. Beta is fairly easy to shield from. A thin sheet of aluminum foil is enough to stop electrons, and so it's still relatively easy to protect yourself from. But beta can be damaging without being internalized. And finally, gamma radiation. Gamma rays are extremely powerful radiation. They are ionizing radiation, which means if they hit an atom, they can turn that atom into an ion. And if they happen to hit the wrong portion of, or the wrong atom inside of one of your cells, they can alter your DNA and potentially cause cancer. And so gamma is that kind of associated cancer threat with radiation. Gamma can also cause skin burns and things like that. These are highly energetic rays. Now, most of them are going to pass right through your body without interacting with any atoms, much like an X-ray would. Think of these as being X-rays, but with even a little bit more juice, kind of even a more energetic ray. And so most of them will pass straight through your body. But if you have a high enough gamma flux, you can get all sorts of kind of real issues going on, both acute, so acute radiation poisoning at the time, and kind of this delayed risk of cancer. Anyway, those are and it's a lot more than I kind of intended to go into just as an intro. So let's get down to the meat of what this video is supposed to be about, which is some practice problems. And if we look at here, I just have a few kind of generalized equations for nuclear decay that we're going to look at. Let's just go ahead and start chopping at them. Sorry, my daughter's making some noise in back of me, so it's got momentarily distracted. Okay, so we've got some tungsten 184, and it's going to decay by alpha. First of all, the symbol for tungsten is a W. The 184 is the mass number, so it goes in that upper left. I can, if I want to, I can put the atomic number for tungsten there. But I don't really have to because, again, tungsten has to be an atomic number. 74 in any periodic table could tell me that. This tungsten, though, is going to decay, and it's going to decay by alpha, and an alpha is a 4,2 helium. Now, the universe practices something called conservation of mass. Whatever number of particles we started this whole nuclear decay with, we still have to end with that many particles. So in the top, out of total nucleons, neutrons and protons, we had 184. If 4 of them got shot out into this helium, there must be 180 of them left. And the same thing for the protons. If we started with 74 of them, and 2 of them got shot out in this helium, there should be left 72 protons. And then we just go back to our periodic table and we find what element is atomic number 72, and we write the appropriate symbol in for that element. And this is now the complete emission, our nuclear equation for the alpha emission from tungsten. Let's take another look at a little bit different decay, a beta decay. And so we're going to start with some sulfur 35. Again, I'm going to put that 35 in the upper left-hand corner. Sulfur's atomic number is 16 if I want to put that down in the bottom. Again, that's kind of optional. And it's going to decay by beta radiation. Beta's our electron with the 0 in the top and the -1 in the bottom. And here's where that -1 is going to come into play. Because this beta emission turns a neutron into a proton, the total number of neutrons and protons doesn't change. One less neutron, one more proton, so the sum of those two things stays the same, 35. That's why we have a 0 in the top. But the number of protons increases by 1 because one of these neutrons was converted into a proton. And so to keep our bookkeeping straight so that we can solve all of these the same way, we put a -1 down here by the electron. So 16, to conserve our numbers, 16 equals -1 plus 17. And you can see then that the actual atomic identity changes here. This becomes a new element that has a new number of protons, 17 protons. And so then we look up the element that has 17 protons, and we find out that that is not, that is chlorine. And there's kind of our sulfur 35 decay by beta. Oh, hold on, let me use this before. Good. Okay. Okay. And sorry, I wanted to get that. I know I've been bad about not shutting my email when I'm making these videos, and so that you get the little notification. So, yeah, random squirrel brain just thought about that while I was making the video. Just thought I'd check it. All right, last one. We've got some gadolinium 148. It's going to decay by alpha, and it's also going to shoot out a beta. Good thing is this beta, oh, excuse me, an alpha and a gamma. Good thing is that this gamma isn't really going to change our problem at all, other than it just needs to be included. Okay, so gadolinium in 148. Symbol is GD, and atomic number is 64, and that's going to decay by alpha. Alpha is this 4,2 helium, and it's also going to shoot out a gamma. So we're going to just write the symbol for a gamma in, and then we have to determine, well, what's our product. And the gamma, again, it kind of has zeros, and you can, if you want, write those in. Zeros in both the top and the bottom, so it doesn't have any effect on the numbers at all. The 148 here has to equal 4 plus 144. And the 64 here has to equal 2 plus 62 here. And so you can see we have some samarium 144 left. At the end of this decay process, some beta or some alpha radiation, some gamma radiation, and some samarium left over. So those are kind of the three classes. Betas increase the proton count by 1, don't affect the mass number at all. Alpha reduces the mass number by 4, reduces the atomic number by 2, and gamma doesn't do anything except just have to be reflected that, hey, this thing's going to shoot some highly energetic rays out, so that might be kind of pertinent to people who are handling that material. That should be it, I think, for a little brief overview of radiation. And you ladies and gentlemen are almost at the end line. If you're watching this video, we have one more video left from the college, and then I don't even think I'm going to do an explanation on that one on my own. I think it's pretty simple material, although I'm going to think about that yet this afternoon and maybe cobble together a little something. Anyway, you're almost done. Summer's almost here, so I hope you're doing well, enjoying yourselves, and staying on top of all your schoolwork. Make sure you get it done and in so I can give you good grades. I know you like me as a teacher, but you don't want to have me again for next year, at least not for this same class.